This observation shows a classic example of platy-ridged lava. Scientists think that this is the same as a lava type called rubbly pahoehoe on Earth. In this lava, a crust of rubble forms as the lava partially cools but then tears up its own cover. Eventually, the rubble can form plates that can be rafted apart as the lava cools further, producing textures like those visible on terrestrial lava lakes that have cooled. Seen here are a complex history of these processes. There are two different shapes of the rubble at right and top left bottom center, indicating two stages of formation. The smooth area at center also is divided into two domains with different polygon styles, indicating that the rift opened, partially cooled, and then opened further. Before collecting a rock sample at a spot nicknamed lifeless, NASA's Perseverance Mars rover employed an abrasion tool to wear down the rock's surface and then used the Planetary Instrument for X-ray Lithochemistry, or PIXL, to study the rock's internal chemistry. This image is composed of multiple shots of the abrasion patch, dubbed Bill's Bay, that were taken on October 2023. Data showed that the rock is rich in carbonates and silica, both of which are ideal for recording paleo-environmental information and preserving signs of ancient life. The rock's sand grains are made of iron-rich carbonate, and the areas between the sand grains are silica, which acts like cement, holding the sand together as a rock. On Earth, both silica and carbonates are good at preserving materials left behind by ancient life. Sand grains made of iron-rich carbonate are also mostly found in places on Earth that are good at protecting carbon-based materials known as organics. Organics can be made from both geological and biological sources. The Lifeless Bay sample does not necessarily show signs of ancient microbial life. Samples like Lifeless Bay would have to be brought back to Earth and studied with complex instruments in laboratories for scientists to confirm signs of ancient life, if indeed they are present. HiRISE and the Context camera, also on board the Mars Reconnaissance Orbiter, are always on the lookout for new impact craters. New impacts can be identified by comparing images of the same region taken at different times, typically years apart, and looking for visual clues of recent impacts. Caltech's camera is more adept at identifying new impacts because of its larger and repeated surface coverage, but HiRISE allows scientists to study those impacts in higher resolution. In this observation, multiple dark spots can be seen corresponding to numerous new craters. Also identifiable is a slightly larger crater and a number of smaller ones, particularly in a cluster next to it. That clustering gives the first indication that these craters were formed in a single event. As the impactor was falling towards Mars, the friction with the atmosphere led to the body fragmenting into smaller pieces shortly before striking the surface, creating this notable pattern. NASA's Ingenuity Mars helicopter is seen here at the starting point of its 47th flight on Mars. This video shows the dust initially kicked up by the helicopter's spinning rotors, as well as Ingenuity taking off, hovering, and beginning its 1,444-foot journey to the southwest. The rotorcraft landed off camera. The video was captured by the Mastcam-Z imager aboard NASA's Perseverance rover. At the time the video was taken, the rover was about 394 feet from the helicopter. In the spring of 2021, the Ingenuity Mars helicopter became the first aircraft to fly on the surface of another planet. When the helicopter lifted off of the Martian surface on April 19, 2021, it marked the beginning of a new era for space exploration. With that first flight, the aerial exploration of Mars had begun, occurring almost 45 years after the Viking landing in 1976. And 24 years after the Mars Pathfinder Sojourner rover mission in 1997, humanity could now robotically explore Mars by air. Some natural phenomena on Mars resemble those on Earth. In certain regions of the red planet, snow falls during winter, much like it does on Earth. With its axial tilt toward the Sun of 25 degrees, close to Earth's current tilt of 23.5 degrees, seasons on Mars are quite dynamic. Changes in season result in changes in weather, surface temperature, and even the distribution of ice on the Martian surface. Mars polar caps essentially have two components, residual and seasonal caps. The residual polar caps are the bulk of the polar cap that persist year after year. While the residual northern polar cap remains pretty consistent over time, the residual southern polar cap, on the other hand, changes quite a bit. The residual northern polar cap is made up predominantly of water ice with some interspersed layers of dust and sand. In the central portion, it is about 2 kilometers thick, on par with the average thickness of the Antarctic ice sheet. The residual cap covers an area nearly twice the size of France, with a volume about half that of the Greenland ice sheet. In winter, however, the areal extent of the cap changes dramatically with the formation of the seasonal polar cap. The seasonal cap forms when carbon dioxide and water vapor in the atmosphere condense onto the Martian surface as frost. Depending on latitude, this frost layer can be up to a meter thick. In 1979, NASA's Viking 2 lander visited the northern plains on Mars and captured a snow-covered surface in the Martian plain known as Utopia Planitia. Immediately after landing, the probe measured the winter temperatures, which was as low as -184 degrees Fahrenheit, and then began photographing the Martian surroundings and transmitting the images back to Earth. Seen here is one of those images which shows a rocky surface covered with a thin layer of snow. While these landscapes closely resemble Earth's snow-covered stony fields, Martian snow has a denser structure than Earth's snow. The snow that falls on Mars consists of frozen carbon dioxide, dry ice. This gives it a texture more similar to solid dry ice than fluffy snowflakes. Snow on Mars also falls exclusively at night, so when temperatures rise, the snow sublimates, releasing carbon dioxide directly into the Martian atmosphere. Another curious fact is that while snow falls on Mars, rain does not. It never rains on the red planet. This is due to the extremely thin layers of the Martian atmosphere. Moreover, the planet lacks a magnetosphere which could shield liquid water from solar radiation. In the absence of a magnetosphere, Mars' surface is constantly exposed to solar radiation and solar wind, making the existence of rain on the planet impossible. The low water content of the Martian atmosphere means that the humidity is also extremely low, making winters there a dry cold. While we typically think of deserts as hot places like the Sahara, the term can refer to cold polar areas that receive little snow or rainfall as well. Conditions on Mars fall into the category of a cold polar desert.